Okay, so the goal today is to finish the portal hub Tall Knuckle. I want to get all the hardware in there to attach the front shell gear housing for the portal to the Tall Knuckle part of the upright for the spindle. And I need to make sure that the steering is going to work where I have it planned and that this lower control arm position is going to work in order to keep that 0-degree kingpin inclination angle. So I made some sketches here to help me visualize the suspension because it's a lot faster than designing all the parts and then in 3D and then cycling them just to find out they're not going to work. Still might not work, but this will give me a better understanding. So this is a trophy truck from BRENTHEL Industries, and they make a four-wheel drive trophy truck with portals, and they claim 26 inches of front wheel travel, which is amazing. That's about plus or minus 20 degrees. I'm going to shoot for plus or minus 30 degrees, and that will give me a lot of wheel travel. So 40 inches of wheel travel. I don't think that's realistic. I think it's probably going to be closer to 25 degrees, which is still 36 inches of wheel travel. But this assembly is like a foot wider than a normal trophy truck. This is the maximum legal width for the highway, which is 8.5 feet wide. So the idea would be you could trailer this without having to get a wide load rating or swapping out for skinny tires. So this is my lower control arm pivot point, which is 8 inches below center. And the upper control arm is way up here with that 0-degree kingpin inclination angle, which means that the upper control arm and the lower control arm pivot points intersect the center line of the wheel. There's a bunch of advantages to that, primarily that have to do with scrub radius. So this sketch down here is as close as I could get to what I think I'm going to build. So this will be easier to see here. So this is the lower control arm. It's going to have these kickdowns to clear the wheel because there's a little bead lock boss on here where the bead lock bolts screw in. And at full compression, I don't want them to interfere with that. The big question mark is it cycles vertically, but what happens when you rotate the tire? So I'll have a better feeling for that once I have it modeled in 3D. But what I think is probably going to happen is that this lower control arm is going to interfere with the rim as you cycle steering at full compression. Pretty rare that you would have full compression and full steering lock, but it all still needs to cycle like that for just best practices for suspension design. This represents the upper control arm pivot point, and I have kind of a is that a trapezoid shape? Parallelogram? What is it? Anyway, whatever this shape is called from geometry class. It's like the most complicated geometry of all time, but I can't remember what this shape is called. So the upper control arms are a little bit narrower, and the reason for that is so that this tire leans in a little bit at compression. So I made this sketch so that I could cycle the suspension up and down by adjusting one of these. So as I increase this, that's 0. That would be ride height. And then this is all the way up. So I could go to 30. That's what I'm going to aim for. I'm going to need a pretty significant cutout here to make room for the, this is where the axle joins the hub. And there's a lot of stuff in the way, so I'm going to have a pretty big beefy cutout here. But I can make some gussets here on the bottom, I think. And then where I have the shocks mounted is 20 inches of shaft length and 36 inches of wheel travel and about, what would that be, 20 minus 4, 16 inches of stroke. So I was actually surprised at how little shock I needed for this. I think it's just by virtue of the fact that it's more than halfway up on the pivot point. So the lever arm chops it in half, so less than half. If it was perfectly half, it would probably be around 16 inches of stroke, but or 18 inches of stroke, but I ended up at 16. So anyway, the other thing that I learned from the guys at Shock Therapy was that, I never knew this, in order to get progressive spring rates as you cycle, at full compression, you want your control arm to be perpendicular with the shock. And then as it goes to full droop, your wheel travels at a progressive rate. So I said that backwards. Starting at full droop, let's go to -30. So starting at full droop, as this wheel moves upward, it's going to move up 1 inch, and this is going to move up less than 1 inch. And then it's going to move up another inch, and this is going to move up a little bit closer to 1 inch. But then by the time you get to full compression on this side, once you're at full compression, then every inch that your control arm moves, your shock moves an equal distance because it's perpendicular to the shock mount. So that's how I got these dimensions here. So this line is fixed to be perpendicular with this line representing the upper control arm. And if I end up needing to adjust the angle here to be less than 30 degrees, I'll probably have to shift these down. But it makes the bulkhead design a lot simpler because I've got this nice little gap here between the upper control arm pivot points on the bulkhead and the shock mounts on the bulkhead. So I'm imagining like a big sheet metal piece that captures all of these. Actually, some of the guys on the trophy truck, like Kibitech in particular, does really cool stuff with billet these days. And he has billet shock mounts. I mean, he has billet everywhere. But he has billet shock mounts on his trailing arms on the rear. So I'm going to see if I can make a billet shock mount for the front bulkhead as well. I think that would be really cool. So that's the suspension geometry that I'm going to start with. The first thing I need to do on the portal hub design is make a cutout when this is at full droop. I need to make a cutout on the back of the tall knuckle that matches this angle, which is 45 degrees, which is actually what I started with originally. So I think it's going to work. Some stuff might get in the way, but I want to remove a bunch of material from that thing anyway because it's incredibly heavy. So that's what I'm going to be starting with. The other consideration is the Ackerman angle. So basically, what that means is, so imagine that this is the rear of the vehicle. As you're turning at full lock, you want your inner tire to be at a sharper angle than the outside tire. The reason for that is that as you turn, this tire, the inside turn tires form an arc and the outside turn tires form an arc, and you want both of those arcs to be concentric. So, for example, you want this to be there and that to be there. Okay, so yeah, that's not actually 100% accurate. You want this to be like that. So anyway, there's a lot of better videos out there explaining Ackerman angle from actual automotive engineers. I just learned about this a couple of days ago. So, trying to figure it out. But I think I got it pretty close. So, these circles represent Heim joints on the steering. And then this 8-inch dimension represents the pivot that goes back and forth. So on trophy trucks, it's swing set steering. On rock crawlers, it's the ram assist, like the hydraulic steering piston. And then these are the steering rods. So in order to get, let's see if that'll work. Okay, that's not going to work. Let's make this super obvious. So in order to get, yeah, I think I had the right idea for this. So I'm going to put this at 1 degree. Otherwise those lines break. So basically what you want is for these two lines from the center of the rear axle to the center of the front wheels. You want the steering pivot points to be as close as possible to that. So, and I don't actually think this is going to work, but I'm going to try it anyway. In order to do that, I had to reduce this dimension a lot. So this Heim is going to cut into the portal hub significantly, but luckily it's an okay place for it to cut in. This dimension here is where I'm going to have problems because the outside diameter of the Heim is going to interfere with the front shell of the portal. But this is theoretically perfect Ackerman. Well, it's not quite perfect, but it's pretty darn close. Because when I move this back to 25-degree steering angle, if it was perfect Ackerman, these guys would be touching each other. The other challenge for this is that the center diff is right here. And in order for everything to be where I want it to be, this steering point is going to interfere with the center diff, especially because it's behind the diff now. Because if I put this in front of the diff, the way it works out, I have reverse Ackerman, which is bad. So I want to avoid that. So I think I'm going to have to increase this dimension a lot, like maybe double it. And I'm going to have to increase this dimension a little bit, so it'll make my Ackerman just slightly worse. But who knows, it might work out. So if I put this at 1, yeah, so let's see what happens. If I make this 6, make this 2, make this 6, and then I need to knock a 1/2 inch off this guy. Cool. This is probably more realistic. 6-inch center offset, 2-inch inboard offset, 6 inches from the center of the diff. It might need to be more. And then if we go to full lock, yeah, so then I'm gonna have interference here. So yeah, this is gonna be tricky. The steering is gonna be tricky for sure. I don't know. Maybe I'll do some crazy offset single arm swing set, like and then a tie rod, like I-beam style tie rod. That might be cool. But this is how the Can-Am Razor steering is designed. It's behind the diff, but they have a little teeny tiny diff because they're running 30-inch tires, not 60-inch tires. So everything's gigantic in here. So anyway, that is the plan for the design. And I'm going to lock in and see how far we get. Okay, so working on the clearance angle for the lower control arm, I'm referencing that sketch that I made to cycle the suspension through, and I added those same dimensions in here to make these clearance cuts on the lower part of the knuckle. So assuming a 35-degree cut there to make 45-degree cut to make room for everything. So this is a complicated part already, and I've already started sort of the process of chasing my tail, trying to make all the features work with each other. So I think this entire part is going to have to be redesigned from the jump. But this exercise will still give me a good idea of whether or not my intended suspension geometry is going to work. Since this part is so far along, I already added a bunch of fillets and chamfers. So I want to make sure that those are all retained and that the part not only looks good, but is machinable. I find that when I'm done with a part, I like to add those chamfers and fillets to make it look visually appealing so that I don't go back and mess with it anymore. And when a part is missing those features, it looks unfinished to me, so it sort of drives me to continue to finish it. So right now I'm just checking the dimensions of the Dana 80 unit bearing. So this would be like an 05 and up Super Duty hub. Those seem to be super popular in the off-road world. I'm figuring out how to bolt that subassembly to the outer shell of the portal. So the portal box is what they call it. So referencing some designs from 74 Weld again and making sure that I have the best hardware possible for this. So the model that I have from 74 Weld uses socket head cap screws. And I don't know why that's the case. It makes more sense to me that you would use hex bolts here because you can put a lot more torque on them. And also grade 8. I don't know if that's available in socket head cap. It's probably not. So the portal box, the outer shell, I need to make some cuts for the gearing, and I want to make sure that I have the right thickness on everything. So the thickness is critical for making sure that there's enough thread engagement on the bolts, because those are the primary load bearing for the unit bearing and the hub portion attaching to the fixed portal box. So I need those to be really strong. Right now what I'm doing is a long process of messing with the gearing dimensions on the portal box, and ultimately I come to the conclusion that I'm just going to put them back the way they were. So they were originally an 8-inch drive gear and then 4-inch input gears. So I tried messing with 7 and 3.5 to retain the 2-to-1 gear reduction. And then I tried, you know, a bunch of dimensions between 7 and 8, and I ended up just going back to 8 because it makes a lot more sense. So the biggest constraint here is the inner dimension of the wheel that sets the outer envelope for this part, and everything in there is really tight. So I had to make this cut so that there's clearance for the output gear. And the issue that I'm having with this part is that there's not enough thickness on the walls to make room for the screw clearances that mount the outer portal box shell to the portal upright. So that's something that I'm going to have to address, and I might revisit that gearing. So I'm making sure I have enough clearance here. I think, oh yeah, SolidWorks is crashing. There we go. We're back. And so these are those really great grade 8 bolts. They're incredibly strong, and I think they're appropriate for automotive applications. So what I need to do next is make sure that my dimensions on the upright match the modifications that I did to the portal box outer shell. And I'm starting now to add the holes for the hardware that's going to bolt those two pieces together. So making sure that I have enough clearance here. That thickness is way too small. So I need to modify some dimensions to make sure that these are all going to work. I'm using 3/8 inch 12-point hardware on this. I really love the way those look. And you can also get safety wired versions of them. The guys at 74 Weld safety wired their 12-point screws for their 4-gear race portal. I don't think they safety wire anything on their street legal portals, but yeah, I'd love to talk to those guys, see if how far off track I am with this design, because I know it's not perfect. Again, this is just basically a mock-up of the portal to make sure that my suspension is going to work. The internals of the portal are just a ton of engineering that I don't think it's necessary for me to redo what they've already done. Yeah, so there's some more bolts there for the bottom. So the way that this works is the top half uses bolts from the outside, the outboard side of the wheel going in, and then on the bottom half you have bolts from the inboard side of the car going in or going out. And so I'm making sure that I have enough clearance here with my existing geometry to make room for those counterbores so that they'll fit, and making sure I'm not going to interfere with any existing features that I want to retain on this part, and also make sure that those holes are actually machinable, you know, because you can't just run a really long drill because they're counterbores, so they have to be flat at the bottom. So you need to make sure that an end mill can actually get in there. And then I don't think you would need a reamer for this because it's not a pinhole, but you want it to be close. So now I'm realizing that the bolts that I've selected were just regular steel and not stainless steel. And so I'm going to have to make sure that those all match. that I'm using the stainless steel ones and that I have enough clearance on the counter bore, which I do not. So I need to increase the ID of that counter bore so that I have clearance for the correct hardware, and then make sure that matches on the other part as well. So yeah, now this is just an exercise in trying to lightweight the part by cutting in some pockets. Since I don't have the gears in there, I don't actually know where the gears would register to, where bearings would be housed, or really anything else. All I know is that I need some bosses here for support, and I need to cut a bunch of material out of this really heavy upright because that bottom portion of it is just a gigantic chunk, and it needs to be hogged out a little bit to reduce some weight. So I'm doing cut offset to surface, which is a really cool feature. And again, I'm not worrying about making everything super easy to machine because this is already like an unbelievably complicated part. So it's going to require a 5-axis and multiple ball end mill operations pretty much no matter what. So trying to make it look as good as possible, be as light as possible, and make sure that it's machinable but not overly simplified. So now I'm chasing my tail again, trying to get these features to match because I have that weird offset there. Not quite what I want. So oftentimes, if you send a part like this to a CNC shop and there's a feature in there that you didn't notice but is not machinable, they will just work around it, and they'll either leave material there that you didn't design, or they'll cut material out that you don't need. So that's it. That's the design.